All right, so good afternoon, everyone, again. So we're just continuing with atomic physics. It's again the shortest topic in physics at this level. Further up you go, it bigger and bigger it gets. So let's revise what we've done so far. Let's zoom out a wee bit. All right, we've looked at atomic notation. We looked at the evolution of the atomic model, how we went from, I'm going back in time here, started off with the plum pudding model by J.J. Thomson. This would have been in the 1880s. Then we had the discovery of the nucleus, which was done by in the Geiger-Mason experiment. This would have been in the 1900s. All right, discovery of the proton was right afterwards. And then we have 1932, James Chadwick discovered or confirmed the presence of the neutron. So that's our basic components of our atom. We're not really required at this level to learn any other subatomic particles. So leave those, they're just for interesting reading. So we have the atomic notation, and now we're going to go on to radioactivity. Numbers at a glance. Did we do this? This look familiar? Anybody? Anyone? You could read it. It's really just something to read. So radioactivity. Everybody, when they hear atomic physics, they think of radioactivity, and your idea and your perception of radioactivity might be a little wrong. All right, because radioactivity is not all that it seems to be. So radioactivity. Let's just get our markers up and ready. Right, so radioactivity. About 100 years ago, Ernest Rutherford and Paul Villard discovered that there were three different types of emissions from radioactive substances. So you see, Ernest Rutherford, he was the man. All right, he was involved in so much research and stuff back then. All right, he's probably the hottest physicist around. Right. So the two of them discovered that there were three different types of emissions from radioactive substances. So they had discovered the radioactive substances. Problem in the 1890s, they had discovered there was this new material that emitted energy that affected photographic paper and whatnot. It was something as simple as that. Somebody wrapped it in a certain paper, brought it close to it, and they destroyed it. Destroyed it being, it then caused it to evaporate into smoke. It doesn't work that way. Right? It caused the photographic paper to get exposed. So it went from dark paper to a bright white circle or something. So that started, again, in this era, really small little things sparked the questions and inquiry into the whole science of the atom. So this is around there here. They had discovered radioactive substances. They discovered that there were different levels of radioactive substances. Some could affect others in different ways, right? Some were really, really spectacular to look at, some not so much. But back then, nobody here knew it was harmful to people. So it was kind of a little dangerous. But they didn't know that as yet. The only time they really learned how dangerous radioactivity was after they dropped the nuclear bombs, which we will touch on in this topic. So going on, continue reading. So there are three different types of radioactive emissions. So this is what we call nuclear radioactive particles. These are particles that are emitted from the nucleus of an atom. All right, this is what we look at in this topic. We don't look at other type of emissions like solar wind and charged particles from big reactions, where we get in space. There are lots of different types of radiation, right? But there are only three different types of radioactive particles that we look at. Right? Radiation is a different word. Radiation doesn't mean what we think it means, but we're going to go through that in a little bit. So three types of emissions are alpha, beta, and gamma radiation. Alpha being first, beta being second, and gamma kind of looks like a curly Y. It's not a Y, right? You just have to kind of draw a little curves in to get your Y. So that's your three emissions. Further experiments show that the alpha and beta emissions are actually particles expelled from the nucleus, as in atomic physics, the party is in the nucleus. Electrons, you have the whole topic of electricity to sit down and be important. But when it comes to atomic physics, the only people we're looking at is within the nucleus itself. So alpha and beta emissions are actually particles. Particles meaning they have mass, they have substance, right? You can actually weigh them and find out charge and whatnot from them, right? Are expelled from the nucleus. Gamma radiation was found to be high energy electromagnetic radiation. So gamma radiation is to the very end of the electromagnetic spectrum. Did we do electromagnetic spectrum in light? We should have. Anybody can remember that? Because we have to learn it anyway. Anyone recall? Okay, if you don't recall, we're going to put it in here and I will save it with that.
Miss Excuse,
Yes.
I noticed that you had a couple of calculations. We don't have any of that.
What calculations?
From the handout, yeah, like all of that, we don't have any.
You know why? Because in Word, when it goes into Google Classroom, it disappears. So, I mean, that's why I usually send you all a PDF, because the PDF keeps the entire document. So I will send you the whole document over in the WhatsApp chat.
Okay, thank you.
All right, because that is what happens with Google. For some reason, Google Classroom just looks at your equation like, I don't like that, no, and it's just get rid of all. So you can imagine what it does to my CAPE handouts. CAPE is nothing but equations. It's just cause the whole thing to go blank. My Form 6 students were very shocked that I sent them an empty handout, because that's not what I do. Right. So if you want to know the electromagnetic spectrum is just a spectrum of electromagnetic energy waves that come out from anything that generates heat and further up, as in all sorts of energy can be expelled out into the air, right, by high energy sources, and there are many layers of your electromagnetic spectrum. So you all should learn what this is. All right, I'm pretty sure I gave it to you in your, when we were doing light, but let's refresh. All right, so that's to cover the largest waves to the smallest waves. So you're going from large waves to very, very small waves. So we have radio waves, microwaves. Those all count as the lower end of the electromagnetic spectrum. Then we have infrared radiation. Infrared radiation, radiate actually just means to spread out in a circular manner. It doesn't mean it's nuclear radiation. It doesn't mean it's radioactive radiation. The word radiation has gotten lost in its proper meaning. So infrared radiation, this is IR, visible light. So I'll call it Roy G. Biv. You all remember what is Roy G. Biv? Anyone? What's Roy G. Biv? It goes with light. Roy G. Biv, somebody.
Red, orange, yellow, green, blue, and purple.
Colors of the rainbow, right? Just they had to give you all. I could play charades, they're all good, you know. Before they want to get Pictionary and charades, all they go win with me, right? Roy G. Biv being the colors of the rainbow, or the colors that make up white light. Remember, white light, which is the light that we get from the sun, right, is white light. But if we split that up, we're going to get our whole spectrum of the rainbow, which will be red, orange, yellow, blue, green, blue, indigo, and violet. After visible light, we have ultraviolet rays. Then we have the ones that are kind of little dangerous will be the upper end of UV, X-rays, and gamma rays. So these are the rays here. These are the electromagnetic spectrum rays that are actually going to cause some sort of danger to us. That wonderful, wonderful nonsense last year of the 5G giving you all radiation poisoning and radiation cancer, 5G actually lies quite here. Nowhere near the dangerous side of the radiation spectrum. It is less energetic than light. It's like telling somebody, you know what, if I shine light in you on your skin, you're going to get cancer, like a light bulb. No. All right, so if anybody heard that nonsense last year that 5G is going to give you cancer, seriously, something wrong with all that. All right, so it's only this top area here, right, which is the very top of ultraviolet. That's why we know ultraviolet radiation, UVA and UVB, right, is the radiation that comes out from the sun. That is what causes skin cancer. You all should know this by now. And then we have UVA, UVC, right? We have different types of ultraviolet radiation, ultraviolet light, a different amount of energy. And the more energetic it is, the more harmful it is to biological cells. But I jump with the gun. That topic is a little later on. So where are gamma rays? Gamma rays are actually quite to the top, to the very end of the electromagnetic spectrum. So it's the most energetic form of energy that exists or that we know of so far. Remember, we only know so much of the universe so far, but we know pretty much, plenty as far as we know, right? The electromagnetic spectrum consists of radio, microwave, infrared, visible, UV, X-rays, and gamma rays. Gamma rays are the ones that we're going to look at right now. Now, these are electromagnetic waves. They exist as waves. So they're not particles that's shooting out to you, right? They have waves. Waves are things that don't have a mass, right? They're not affected by magnetic fields and whatnot. So knowing that, let's continue reading. When radioactive decay occurs, the original atom spontaneously changes into an atom of a different element. Nature was already doing what alchemists had so fruitlessly tried to do. You all ever heard of what an alchemist? You all know what this is or what these people try to do? Anyone? Nobody. All right, that's fine. You all knew that, or you all know that the birth topic of astronomy was astrology, right? As in long ago, they thought, that the stars has a plan written for the people, and where the stars are, it's going to influence how people run. So that's why they hired a whole bunch of, back then it was philosophers and people who could investigate how stars run to try to inform the king and the kingdoms and rulers and priests and emperors and all those people. If you all know how to read the stars properly, you'll be able to predict how life runs. Now, in no time at all, they realized that the connection between the stars and how people's lives were absolutely not related. They went from astrology and ended up developing astronomy. Now, alchemy is somewhat similar, but this is the chemistry, right? Alchemy, way back in the Middle Ages, they thought that there was a special formula that you could have used, or a special chemical reaction, or special process or ritual or something that can be used to turn anything into gold. This was the idea that back then. It's outlandish as thinking that the stars are going to tell you what happened until tomorrow, right? But they thought that there was some special ritual and some special reaction that you can run things through to make anything turn into gold. So that means they can make my graphic pen into gold, right? My medical tape here into gold. And so from that, they started doing chemical reactions. They start playing with chemistry, they start playing with chemicals, and they realize, you know what, this is looking to right, you know, but in the process, from alchemy was born chemistry. So what they had tried to do, what alchemists had tried to do, they had tried to turn the element, one element into another, and that other element was gold. So even though this is more than just gold, so what alchemists were trying to do, of course, they failed spectacularly. Right? The people who got famous are those who cheated and put gold into their pots and say that they made it gold. Right? So nature was already doing what alchemists had so fruitlessly tried to do. So nature by itself, the way how radioactivity works, anytime we have, it usually works with a bigger atom. Anytime we have a big atom, right? And this big atom has an unstable nucleus, as in the nucleus is just not very, right? The nucleus is unstable. What it's going to do, anytime it is unstable, it's going to try to get rid of that excess energy. So it's going to shoot out some little particle, right? It's going to shoot out some other particle, or it's going to give off energy in some other way in the hope of settling down. That is the whole reason we have radioactive particles and emissions occurring, because you have an unstable atom that wants to occupy the lowest energy state possible. And to do that, it's going to try to spit out as much stuff from the nucleus, because the nucleus is what holds all the energy in the atom. All right, so it tries to get rid of all of that negative energy to settle down. And in the process of doing that, we're going to go from one element, all right, so you can go from uranium to radium or something. All right, so just by spitting out or ejecting or firing out some of these particles, an element is going to change. So this is something that happens in nature. You cannot do a chemical reaction to make radioactive chemicals or to make radioactive decay. We cannot do it. The material itself does it. All right, we're not that powerful. So continue reading. Scientists such as Ernest Rutherford quickly made use of these new particles to investigate the nature of matter, as we did last week. They used the alpha particle, right, to discover the nucleus. Now, of course, you know, that wasn't the purpose of the experiment, but that's what ended up happening. They used all these little particles to perform experiments, right, and whatnot. So later on, scientists also use them to create new isotopes. So let's continue reading. So we're going to look at our 3 alpha emissions, 3 radioactive emissions, sorry. So we have alpha decay. So we're going to look at alpha particles. Now, why do I call it decay? You're going to see I'm using the word decay. Now, when something is decaying, it's basically breaking down. And our radioactive emissions are only given off when an unstable atom is breaking down into a more stable substance, a more stable entity. So we call it decay because it's something that's being broken down. No, we cannot actually take an alpha particle and shoot it into something and it's going to absorb it. Doesn't work that way. All right, does not work that way at all. This is something that's given off, right, in a hope to get nice and stable. Right, so let's read. When a heavy nucleus is undergoing radioactive decay, it may eject an alpha particle, maybe not always, but sometimes. An alpha particle is a positively charged chunk of matter. It consists of 2 protons and 2 neutrons that have been ejected from the nucleus of a radioactive atom. An alpha particle is identical to a helium nucleus and can also be written as, so we're going to look at the 2 ways we can write an alpha particle. An alpha particle, ideally, this is the best way to write it, is alpha particle has 4 particles in it, being 2 protons and 2 neutrons, right? So it has a alpha 4-2, because that is what is actually happening. If you have here, right, and that makes sense. Suppose we have something like radium. Radium, in the hope to get rid of this unnecessary energy, because again, everything wants to occupy the lowest energy state possible, it's going to want to get rid of some of its energy. So what it does, it fires out one of these alpha particles. All right, so one of these alpha particles will be inside of the nucleus, and to get rid of that energy, it just fires it out. That's all it does. It just spits it out or ejects it out. It's not like, you know, that radium is now going to go and look for helium nucleus. Radium doesn't have helium in it, right? What it does have, it has protons and neutrons. And what does a helium nucleus look like essentially? This is just to make people remember it better, but I think this is just confusing you all, right? A helium nucleus, we know helium has 2 protons, 2 neutrons, and 2 electrons. So be 4 and 2, and if it was neutrally charged, this will be a 0. But since it is just the nucleus, we know it has no electrons. So that means if you have no electrons, this +2 here will not balance out with anybody, and it will now have a +2 charge. Everybody okay with that? I'll say it again. I think I will move on. All right, so what an alpha particle is, it's simply an unstable nucleus that fires out a little packet of energy, and that packet of energy happens to be 2 protons and 2 neutrons flying out at very high speed. When you always see how fast these things move. So that's alpha decay. Alpha decay is simply a radioactive or unstable atom that sheds 2 protons and 2 neutrons in one little ball of emission. Next one here, now this one tends to be a little bit confusing, but you have to kind of bear with it. It's 2 lines here, but it's a little bit confusing. Beta decay, right? Beta are electrons. Essentially, the physics of a beta particle is an electron. It has the mass of an electron. It has a charge of an electron. It behaves like an electron, but is it an electron? Nuh-uh. Nope. What they are actually electrons that have originated within the nucleus of a radioactive atom and not the electron cloud. So what it actually is, all right, the atom is far more complex than you all could dare to imagine. What it does, the universe operates in what we call balance of opposites, meaning if there's a positive in something here, there must be a negative somewhere out around or close by or whatever to maintain balance. So the same thing happens if we have an electron. So that is big high physics. I don't know who the people who found this out and how their mind must have been blown. Right, so that's our electron shell. There are electrons in, you know, outside of the nucleus. Right, and inside of the nucleus, right, yes, we're going to have our 2 positives, and then we're going to have our 2 neutral charges. But because we have these 2 negative charges in here, right, there are also, to keep the atom bonded, particles that look like an electron inside of the nucleus. Because what is keeping this nucleus together? If I have 2 positive charges, just to tell you how they had to sit down and really investigate this. If I have 2 positive charges inside of the nucleus, what on earth is keeping that nucleus together? Considering they have the same charge, they will not be attracted to each other. You all realize how complicated this whole world is, right? Not just the world, the universe. All right, so what they are, they're actually little tiny little stuff inside of the nucleus that both exist in both positive and negative versions of each other. So if we have positive, we have protons, we will have something called like an, almost like an antiproton. There will be something that looks like an electron that resides in the nucleus. Because it's contained in the nucleus itself, and it's not involved in any of the bonding or any of the chemical reactions, anything at all, we don't really consider it. But there are negatively charged little teeny tiny things in the nucleus that carries a lot of energy that can be emitted during radioactive decay. And those are beta particles. Beta particles are not electrons from the shell, but they are particles that are basically identical in behavior to an electron. All right, it's not saying it's a shell electron. All right, remember we call this your valence shell. All right, this is your valence shell meant for valence bonding or ionic bonding. It is not a valence electron. It is a particle that is similar to the electron that's found within the nucleus itself. Everybody follow that so far? Wasn't too confusing? They're never going to ask you to explain what a beta particle is, how it came to be. They're just going to ask you to know, one, what it is and how it changes the atom. That's all they're going to ever ask you to do. So your beta particle, how do you write the symbol? The beta particle is B minus 1. So here it means, B means there are no particles emitted from the nucleus, essentially, right? So there are no protons and no neutrons, 0 protons and 0 neutrons. But what it has here, it has a particle that has a -1 charge, but because it lies within, or it's closer, it's the opposite of a proton. Remember, proton is positively charged. Your beta particle has a -1 charge. That -1 charge we will use in mathematics coming down to work out our equations and balance our equations. All right, so this indicates that you have a negative proton. Why is it a negative proton? Because it's not really a proton, right? And it's not an electron. Electrons lie at the top here. It's not an electron that comes from the electron shell, right? But it's something to the opposite of a proton. All right, it just has a negative charge. So just bear with it as it goes. And lastly, we have gamma emission. Gamma emission, with some nuclides, the emission of an alpha or beta particle from the nucleus leave the protons and neutrons in an excited arrangement with more energy than normal. So even that, you would think that you have this atom, right? It has gone, take that atom, you have your nucleus, right? It has fired out an alpha particle to suck away some of that negative energy. But because we had fired out that alpha particle, everything now is going to get kind of jumbled, right? Because now we end up mixing up the stuff in the nucleus, and it still is an excited state. It's probably more excited than it was before, right? You all know about Jenga, right? Everybody's played the game Jenga or know what it is. Yeah, well, it should. All right, you know, that's a game where you have a whole bunch of blocks stacked up on top of each other, and then you have to take out a block without it having to fall. When you end up taking out a block in Jenga, right, the chances are, right, if you take out one of these blocks, right, you take out one of those blocks, maybe the system will fall down, or maybe it will remain the same. But you know, there's just one block in Jenga. If you take out that one block, you call the whole system to destabilize. That's basically what's happening here. When we take out an alpha particle from an atom, we kind of destabilize it a little bit more because we're taking out one of the building blocks, right? It is meant to have the 4 and the 2 protons and 2 neutrons. Why are you taking this out? So in order to settle down, it is going to get rid of more energy. And what does it do? It ends up, okay, I have to continue reading, right? As the photons and neutrons rearrange to become more stable, they lose energy, which is emitted as a photon of gamma radiation. A photon is basically a packet of energy, a packet of electromagnetic energy. So light emits photons. Light is carried by photons. That's why we always say a photon of light. But a photon is essentially a little packet of energy of any form of electromagnetic radiation, which could be, you know, radio waves, right? Infrared, light, UV, X-ray, gamma. Any of these emit energy in what we call photons. So in order for your atom to stabilize itself and to get nice and settled, right, it's just going to shoot out a photon of radioactive, of gamma radiation. Gamma rays are the most energetic form of electromagnetic waves, right, with the highest frequency. There's nothing higher, naturally, any kind of wave that has a frequency higher than gamma rays, the highest form of energy in the that we know of so far in the universe. Since they are waves, there is no mass nor charge associated with gamma rays. Now, if you look at the names of these things, they always say alpha particle, beta particle, and gamma ray. Why? Because alpha and beta are particles. They are actual material components of material. A gamma ray is just a ray of energy coming out of your nucleus. So let's look at the comparison of the three. All right, so we have alpha, beta, and gamma. We can look at charge, relative mass, ionizing powder, since you all are power. Did I say powder? I think I did. All right, ionizing power, penetrative power, effective magnetic field, and speed. So alpha particles have a +2 charge. Why do I have a +2 charge? Because they have 2 protons. All right, then we have the relative mass. Hold on. All right, so the relative mass of an alpha particle is 4 times that of a proton. So basically it's going to be 2 protons plus 2 neutrons. So it's 5,700 times heavier than an electron. This is what we talk about relative mass to an electron. Ionizing power, it is going to have a very strong ionizing power. Why is that? It has a +2 charge. And if it has a +2 charge, any atom it passes by that has a somewhat weaker electron, guess what? That electron, you're coming with me. It's going to pull electrons or displace electrons everywhere it passes. And because it moves really fast, that electron doesn't even know, you know, that it was around. It just displaces it. So it has a very, very strong, right? This is what makes it very dangerous. Right? It has a very strong ionizing power. Imagine, just jumping the gun again, alpha decay, alpha radiation that has the ability to pull out electrons. Guess what it will do to the atoms in your cells? The atoms in the cells in your hand, in your body, whatever. Think about the terrorizing, the catastrophic damage that can have on your cells, knowing that, number one, it can pass through the body, well, pass through a little bit of the body, at least the skin. But everywhere it passes, it's going to cause all the electrons in its path to get disrupted or probably come out of the atom that makes up the cells. Think about how catastrophic that is. You all could kind of wrap your brains around that, because we're going to have to look at the dangers of radioactivity lower down. All right, so because it has a very, very strong ionizing power, that's why it tends to be pretty dangerous. It can be stopped by paper. So you know what? Yeah, we could hold up a piece of paper in front of an alpha particle. All right. I will check to see if our Geiger counter is working, because we do have alpha, beta, and gamma sources in school. Right? Don't worry, it's not dangerous. All right, it's the smallest little drop of stuff. All right, so it can be stopped by paper. So a single sheet of paper, if you take that paper, of course, it's a very big source, it's not going to help, but if you get a little source and we just take a little sheet of paper, put it on top of it, it should stop the radiation from flowing. All right, now people are going to ask, Miss, that don't sound so dangerous, but when you have a bomb, or you have a material here that's just giving off invisible radiation every single second for hundreds of years, probably, you wouldn't know to cover it with paper. You wouldn't even know it was there. All right, so continue reading. Alpha particles are deflected by magnetic fields. So magnetic fields deflect positive charges, and the speed is 1/10 the speed of light. That's still pretty fast, because remember the speed of light? Anybody can recall the speed of light? Anybody? Okay, nobody. All right, light has a speed of 3 by 10 to the 8 meters per second, or 300,000 kilometers in a second. So while that doesn't, 1/10 doesn't sound so bad. Yeah, it's a decimal, but guess what? It's traveling 30,000 kilometers in 1 second. That's still pretty fast, y'all. That's still really, really fast. So once it's firing out or coming out of a particle, that's the speed it's going to travel at, 1/10 the speed of light. It travels very fast, which is what makes it dangerous. So even though it can be stopped by paper, because it's traveling so fast, y'all could probably penetrate through paper, because it's moving that fast. Next one, beta particles. Beta particles have a charge of -1. It has the mass of an electron, so it has a relative mass of 1 to an electron. It has a weak ionizing power, because electrons don't really ionize as strongly as positive charges, because everything has electrons on the outside of it. All right, so it's not going to really disrupt. So suppose you have an atom here with electrons on the outside. It has electrons on the outside, right? Let's do a 4-shell, 8-shell electron. If I took a positive charge and passed it through it, so I had a positive 2 charge, guess what? Some of those electrons are going to get pulled and attracted by that very strong +2 charge. But what's going to happen now if I have an electron passing by? They're just going to get a little repelled. Now they're going to get repelled so little bit. Why? Because they're already surrounded by electrons. All right. So the ionizing power of beta radiation or beta particles is not that much, but it's still a little. We're going to see why beta particles end up being dangerous radioactively. It can be stopped by 2 or 3 centimeters of aluminum. So 2 or 3 centimeters thicker. Meaning if you get aluminum, that's 2 or 3 centimeters thick, which is pretty thick. That's about the entire length from the top of your thumb to the first little marking on your thumb, 2 or 3 centimeters, that thick. A sheet of like that of aluminum will stop it. Beta particles are attracted to a magnetic field. It moves nearly at the speed of light, nearly. So you're fast, it's real fast. Then we have gamma rays. Remember gamma written like a little curly Y kind of thing. Practice writing it, please. Do not write it as a Y. Do a little curly gamma rays. There is no charge in a gamma ray. There's no relative mass in a gamma ray. It has no ionizing power. If it has no charge, it cannot ionize. So let's just look here. Half of your gamma rays will be stopped by 5 centimeters of lead. So imagine how thick lead is. Imagine how heavy lead is. So if I were to put a wall, just to show you, how, again, it's dangerous. If I put a wall of 5 centimeters, do I have a ruler to actually measure out 5 centimeters on the screen? Right, 5 centimeters. If I had a wall of 5 centimeters thick of lead, right, heavy, solid lead, right? Of course, lead is far thicker and far denser and far stronger than concrete. If I were to fire gamma rays into that 5 centimeters of lead, only half of the gamma rays will get stopped. The rest will still pass through. And imagine these things are not moving in 3, 4, they're moving in billions of rays, trillions of rays. So lead, yeah, it does the job to stop some of it, but not all. And then is it attracted to a magnetic field? No, it has no charge. It has no positive pole, no negative pole, no dipoles, no monopoles. It's poleless. Right? So gamma rays are not affected by magnetic fields. And since they are electromagnetic waves, all electromagnetic waves travel at the speed of light, not just light travels at the speed of light. So this travels at the speed of light. So even though gamma rays don't sound like much, number one, the most energetic form of energy in the universe, you basically can't stop it, and it travels at the speed of light. Yeah, right? So it makes up for what the others can do. The others have all kind of charge and mass and whatnot. The gamma rays pack a pretty big punch, and we're going to learn the horrors of gamma ray radiation poisoning and what this actually does to human beings and biological cells in the next class. Right? If you're kind of grossed out and whatever by descriptions, I'm warning you, the next one might be a little scary. All right, so we're going to wrap up there. So we have the K equations. We're going to do that next day. Let me write that down. That's where we reach. So at least I'll remember. Stopped before the K. All right, so we will stop there. Next day, we will do the K equations. All right, so it's not much. The K equations are really easy and really fun. Yeah, my idea of fun is weird. All right, we're going to look into half-life. Oh, we didn't reach half-life. The next lab we're doing is going to be half-life. But if you give it a read, it's explained here what half-life is. So read the handout. I'm going to post this up in the WhatsApp chat, and then I'm going to make a what you may call it, a PDF and put it in Google Classroom. So at least you'll get the equations. So you can read this up. All right, so next class we'll be doing the K equations, half-life, nuclear energy. All right, and then we will finish up that topic. And then you'll get some videos and whatnot. Now, in this topic, there's some reading topics you're meant to go and do. So I'm going to have to give you that as homework. There's no reason I have to explain that out. Homework-wise, you all have to go and read up. Why has it disappeared? It disappeared, y'all. All right, you all have to read up the use of radioactive materials in industry and medicine, because we do have some radioactive materials that we use in medicine. All right, we do have things like x-rays and stuff that we use extensively in medicine. All right, and whatnot. You have to learn what it does, and you have to learn safety procedures. So you're going to get that, what you have to read later on, and whatnot. So just to wrap up, that's what we did today. Wednesday, when I see you all, we are going to be doing IV characteristics of a conductor, meaning we're looking at the current and voltage of a conductor. We're going to be working out an analog version of half-life. No, we're not using anything radioactive. No, you don't. All right. And then the following week or whenever, I will look at everyone's schedule and I will call everyone back in for those who have to finish up your other labs. The only 2 labs we're coming back out here to finish or to do, again, I have the list here, are the foil lab, which was what you would have done in Form 4, and the focal length lab. Everybody here finished the reflection and refraction lab, so that's fine. Those are the only labs we have left to do, right, to complete our SBAs for 2021. The other labs did not contribute to your SBA because CXC released which labs we have to, which general type of labs we had to use for your SBA. All right, everyone okay with that? Yeah?
Yes, yes.
All right, cool. All right, so let me stop the recording.